In this week, I'm going to give you an introductory lectures on sequentially generative AI. So the title of the class today is Today and Wednesday, I'm going to focus on the basic architecture of sequential generative AI. And as an example, I'm going to give you a lecture on the current neural network. And after a break of Chuseok, I'm going to move to the transformer model. Transformer model is the core part of GPT. I think, in my opinion, there are two different types of generative AI. One of them is sequential data generation, and it includes text, sound, and voice. In other words, in this class and Wednesday class, I'm going to give you the overall architecture and backpropagation principles and loss functions associated with sequential data generation. Every human being has a face. You may have an ear, you may have an eyes, and you have nose and mouth. Our human has to interact with the other people or nature or environment. One of them is through an ear. We have to listen, voice, and sound. That means because our bandwidth of voice is very narrow, very small, we have to send information serially. I am a boy. I am a boy. So, because we have to send certain amount of information to human or to other humans, because our sound has very limited bandwidth. In order to send certain amount, we have to have a serial information. We have to serialize our thinking, and we have to send them to others. Ear and sound has such sequential data form. Another type of data generated by AI could be a form of image data. Image has very high bandwidth information because in a second we can detect many information by using your eye. So it is related to the eye. Sometime in the future, I think we will have a new generative AI which can generate sequential data and image data simultaneously. That is what I'm asking or what I'm imagining generative AI in 10 years later. Of course, we need huge amount of sequential data and image data and AI supercomputers in order to do that. I think this is the way roadmap I may have. So in order to develop this, so if we have this kind of generative AI, we can make a movie. I also suggest generative AI architecture in order to achieve this kind of multimodal generative AI. This is my imagination. We have an encoder we're gonna put text. We can write a text and it will be encoded by using this encoder, and output encoder may have certain summarized information that is being called as latent vector. It is not easy to explain why we may need G space. There are certain explanations. One of them is our text has so much information, we have to reduce that information into small vector space. Probably G space is more reality of our nature. It has probability distributions and it has certain symbolic representations. And output will be supplied to probably 3 different decoder. First one is text decoder. Second decoder is for image. Third decoder maybe for sound. All this decoder output may be combined to become multimodal output. Of course, this diagram represents conceptual block diagram and architecture of multimodal generative AI. Of course, all this decoder output has to be synchronized. Text, image, and sound has to be synchronized. That is my vision of future generative AI. In order to do that, we have to decide deep neural network architecture of decoder. Also, we have to develop or study DNN architecture of each decoders. Also, we have to be able to find a loss function and back propagation chain rules. Even though this becomes complicated, we still need loss function for each decoder output. And by defining decoder outputs and by applying gradient descent algorithm, we have to optimize DNN model parameters. In some way, we have to optimize this architecture. If this architecture is very simple, we can sometimes use our mathematical background to optimize this architecture and hyperparameters. But if this model parameter is becoming 100 and 1,000 million parameters, usually mathematics may not be enough, or traditional optimization method may not be enough to optimize this architecture and loss function. Even loss function has to be optimized. We don't know what would be the best loss function. So in order to optimize whole this architecture, I believe that we need to have some feedback structure. I think that in that purpose, the reinforcement learning algorithm may be used. So in this class, after a week, I'm going to introduce generative AI who has the encoder G and decoder architecture, who is suitable for text, who is suitable for image, and who is suitable for sound. Probably 3 years later, if I give you a lecture, I may give you a new idea to combine all of them together to make a single multimodal generative AI. But please remember that in the reinforcement learning, we have to define the word. That is very core part of the reinforcement learning, and probably in the last week of October, I'm going to heavily talk about the reinforcement learning and the word. Who is gonna define this reward? Human being or AI? Probably God, or Earth, or nature, or space. Someone else who is living in the heaven may have to decide this one. In these days, there are some disputes about ethics of AI. Who is controlling the AI? Human or AI itself? If human want to control the AI, they have to control the world. And probably some loss function. The only rest of the work will be done by computers and AI semiconductors. I imagine that only two things human can control AI is reward in feedback architecture and loss function at the end of generative AI. Now, usually we are communicating with computer with the text or voice. Sometimes we are speaking or sometimes we are typing the keyboard. But our output system from our human being is usually the text or voice. Some artists can draw a picture, but it takes some time, an hour or a day. Instantaneous communication is through a text or voice. That's why I usually prefer to have text as an input of generative AI. But somehow, when we are encoding our text into G space, we found that some of the information are lost. By manipulating the data and generation process in G space, it is efficient because the dimension of G vector is much smaller than text vector space. So it is very efficient using the GPU and AI supercomputers. But what we found, not me, but some scientists found and AI engineers found that some informations are lost during the encoding and decoding process. So sometimes we have to connect information of our text directly to the encoder, not through G-space. That is called as an attention. Attention network, so we're gonna have another network, DNN network, that is designed for attention. It is a kind of face-to-face meet. During the Corona period, I met students through using the Zoom. But sometimes we want to see face-to-face. This is a kind of face-to-face meeting. This is a kind of Zoom meeting. So attention network is very, very core part of transformer model. ChatGPT are writing texts as if he is a human. It is very difficult to distinguish ChatGPT or real human. They are writing text very freely and naturally. One of them is key part is attention network. Second important contribution of transformer model is positional encoding. When we are writing a sentence, depending on the position of each word, sometimes meanings are completely different. Somehow we are expressing our thinking by changing the order of the word in a sentence. Somehow our language has an important meaning at a position. So another important feature that was included in the transformer model GPT is positional encoding. When we are speaking, each word is encoded by word embedding process. Because our computer does not understand our language, we have to encode our language into the digital form. In those processes, we are adding positional information in each word. I am a boy, am I a boy? Two different meaning and two different, probably sometimes in a poem we are put some words ahead of others. So positional encoding is important thing. Third one is parallel processing. Even though we are generating text sequentially, but those whole text and sentence or book is inputted into encoder simultaneously. And output of text is not sequential. Simultaneously it generates the whole text. Why is that? Because we want to minimize the latency between human and computer. Let's assume what is your name and put into the AI computer. If the reply takes an hour, it is useless. It has come back in a millisecond. People are not patient enough. So whole this architecture has to be processed in parallel processing. Encoder, latent space, and decoder is sequential. But input of whole text or book or whole internet document will be inputted into encoder in parallel. Output will be in parallel. Whole movie will be generated simultaneously in a second. That is the requirement of business of generative AI. That's why our GPT architecture should be parallel and our AI computer should be parallel. So parallelism of this architecture and data processing, encoding, decoding, and computing is the most important requirement of generative AI. So when you are designing new AI computers or AI package or AI chip, memory effect and multiplication effect combined together, it doesn't matter that much. How much those elements could be aligned in parallel, and they are calculating and memorizing them in parallel with the synchronization. Synchronization means picosecond level or nanosecond level. Rather than having a single core or 64 cores, 1,000 and million cores are much more beneficial for this architecture, and they have to match, they have to add, multiply, and so on, have to synchronize together. How can we synchronize each devices together? We have to have a same clock, but clock propagation, signal clock propagation will be controlled by speed of light. We cannot go faster than that. And with the given speed of light, how can we synchronize them? We have to make the same length of interconnection. Those are another subject of next semester class. Now, one of the examples of this text encoder decoder will be RNN. In this week, I'm going to give you a lecture on the current network that is very initial generative AI model suitable for text and text generation. And probably after Chuseok break, we're gonna move on to the architecture, loss function, and backpropagation of transform model. And in the middle of October, I'm going to talk about image decoder and sound decoder and so on. So now I will move on to the current neural network. It is a little bit old model, but still it is good to talk about them. Good morning. This RNN is very initial sequential generative AI. Input text will be decomposed into a sequential form. 1, 2, T is the time step. If you put into a whole textbook, this T may be a million number. Each X could represent a word. I am a boy, something like that. I'm studying at KAIST. So each input will go into your neural network. Actually, this part is encoder. This part is decoder. Your input will be inputted into decoder, and you're gonna have hidden layer 1. H means hidden layer output. E means encoder. Again, transformer model that is a basic architecture for GPT is a little bit more complicated. But let's start with a little bit fundamental architecture that is called as recurrent neural network. In the recurrent neural network, I can give you loss function and I can derive equations for backpropagations. But transform model is much more complicated. I'm not going to do that. So this recurrent neural network is more suitable for educational purpose. So when we are putting the input vectors sequentially, hidden layer information is transmitted to next hidden layer. First step hidden layer information is transmitted to the second hidden layer that is multiplied by second stage input. And so sequentially more information is added in the hidden layer, and after the time step t, the hidden layer output is transmitted to latent vector space G. So of course, G has to be a certain amount of size to contain all these informations. But let's assume that this time step t is like a million or billions. Then initial information are quite lost, because so many multiplication with matrix multiplication. This hidden layer, this architecture will be made by deep neural network. There are so many big size of weight vectors. This output of latent specs will be inputted into the input of decoder, and we may have decoder hidden layer, in each step of decoder we're gonna have output at each step. So let's assume X input vector is Korean language. Output Y will be English translation. So if I give you an English, probably they may improve my English with a better grammar or expressions. So text to text, or Y could be an images. Sequence of images like a webtoon, or this sequence of Y could be sound. If I input a text, please make music of autumn leaves. Probably this Y1, Y2, Y3 could be a sound sequence. I think this kind of architecture was called as a large language model. Using this basic encoder latent specs and the decoder architecture, if we add attention network that directly connect between encoder and decoder, if we have a positional encoding, if we add positional information in each input vectors, and if these X are input in parallel simultaneously and output will be generated in parallel. That is the core part of transformer model. But before going into this transformer model, so after Chuseok break, I'm going to give lectures on this, a class about attention, a class about positioning encoding, a class about parallel processing. But today, I'm going to talk about recurrent neural network. This is the overall architecture of recurrent network. And specifically, in some case, encoder and decoder are combined together. And this G vector is hidden inside hidden layers. That is a recurrent network, and I'm going to give you the lectures on recurrent neural network. Yes, I'm going to give you a lecture on architecture, activation function, loss function, and backpropagation. That will be the core part of class today and Wednesday. Especially recurrent neural network has this kind of architecture, but more likely encoder and decoder are combined together to a single form. In the recurrent neural network, we have input, we have step 1 hidden layer, step 2 hidden layer, step 3 hidden layer, and it will be connected to up to the terminal. Time step, you have input vector x1, x2, x3, and xt. Your input will be connected to hidden layer by using U matrix. Your input vector, your sentence or wording will be converted to a vector forms by using word embedding. Your input vector of each sequence will be input to the hidden layer by multiplying the U matrix. I think U matrix could be a kind of bridge between your input data to the encoder decoder. Interesting is you are sharing same U vectors, U matrices. And of course, in the U matrix, you this will be, there will be some weight matrices, and you have to find them during the backpropagation. The hidden layer information is connected to second hidden layer by multiplying W matrix. And each step of hidden layer transmission from previous time step to next time step, we are multiplying it with W. So backpropagation and training means that we have to determine optimal matrix of U and W. Of course, in these days, we are mostly using the ChatGPT type of transformer model to convert text to text and something like that. RNN may not be no longer used, but it is good for educational purpose. Without talking about this RNN, it is almost impossible to talk about transformer model. Hidden layer output is connected to real output using V matrix. So if X sequence is Korean language, I'm a boy, this Y sentence could be English translation of input. Somehow it works. Not as good as transformer model. So during the training process of this RNN network, what our goal is to determine matrix element of U, W, and V. In order to do that, we have to define loss function. Actually, we're going to have Y-1, Y-2, Y-3, and Y-T. The difference between Y dash may be a good English translation, like, and Y is an output of RNN network. By comparing these two, we can define a loss function. Usually, in this RNN architecture, we are using entropy function. That's why we spend so many classes to talk about entropy and KL divergences. And if you define the loss function, then you can induce equations to define backpropagation. And during the backpropagation, we optimize V, W, and U. On Wednesday, I'm going to drive those equations. So X is an input layer. H is hidden layer. Y is output layer. One particular feature of this RNN network is that we have time step T. And this matrix W, H, and V are sequentially come back again and again. So it recurrent again and again. Again, previous hidden layer information is conveyed to the next level sequentially. But basically, U matrix, V matrix, and deep neural network are repeatedly used again and again. That's why we call it recurrent neural network. If we have a single neural network, it is used again and again and again. That's why it is saying recurrent neural network. But connecting between previous neural network and next neural network is by having this connection matrix W. Sequentially, more and more information of input will be accumulated up to the terminal final stage. And sometimes output can be a sequential, or sometimes this could be connected to another decoder or something like that. So there might be many variations. I told you that when we are connecting input vector to the hidden layer to hidden layer to output, we have to have a neural network. That means we have to define activation function. And here activation function is used for tangent hyperbolic function. It is a little bit of a variation of sigmoid function. You remember that sigmoid function is between 0 to 1. You remember that? And tangent hyperbolic function is between -1 to 1. Not much big difference between sigmoid and tangent hyperbolic function. But so far, most of the recurrent neural network are using tangent hyperbolic function as an activation function. Tangent hyperbolic function is, this sigmoid function is kind of something like that, and tangent hyperbolic function, it has a form of why is the activation function is so important? Basically, deep neural network has perceptron, and output of perceptron has to have certain nonlinear function. I think that is the property of our synapse in our brain. There might be many different ways to define that, but very similar functions. One day I was imagining that why it has -1 to 1, probably -1 means the past. Past information, 1 means the future information. Because this is a time sequence. If I'm standing here, this is the past information, this one is the future information. So that's my philosophical interpretation. I may be wrong, but that's why we may have minus and 1. When we are generating images, probably we're going to use a sigmoid function. Image does not have past and future. It has just one shot. Probably that's why we have 0 to 1. I may be wrong. And as a loss of this deep neural network, we're going to use the entropy function. And at some point, we're going to use the softmax function as well. Softmax function means that output of y is equal to 1. It's a kind of regularization. Let's assume that we have output vector y, y2, y3 in time step. Each summation of each element of each vector should be equal to 1. That reinforcement learning. Let's assume we have 10 students in a class. I may give you 1 point to a student, another student 1 point, 1 point. Then entropy is very high. And in some case, I may give you a 10 point to a student, rest of them are just 0 student. That is the extreme case of low entropy. That is what the target of this backpropagation. But anyway, summation of the score of all the students is always 10. That is the softmax reinforcement. And I'm going to come back this again. So let's shortly thinking about the dimension of matrices. Let's assume that each input vector x that represents a text or a word or sentence or whatever, each input will have certain vector form, and we are assuming that the vector size of input is D, 1 by D by 1 matrix. And hidden layer information that is also a form of vector, I assume that has size of P by 1. And then this U matrix will convert X input information to hidden layer. So because of that, this U matrix has a size of P multiplied by D. Of course, H has a form of T, time step T. At each time step T, we have input vector of size D, and output of input multiplied by U matrix will become a hidden layer vector that has size of P. In each step, X vector will different and hidden layer will be different. And we have a single U matrix that will convert input vector to hidden layer. Hidden layer has a form of I'm sorry, this is a little bit complicated mathematical representations, but meaning is not that difficult to understand. I'm just trying to express this whole RNN architecture as a form of equation. Now, what is hidden layer? Hidden layer has certain column. Its activation function of intermediate state. What is the intermediate state? Multiplication of current input vector xt multiplied by U matrix. So by multiplying this uj multiplied by input is gonna give you hjt. This is something like matrix multiplication. Plus W multiplied previous hidden state. Previous hidden state is multiplied by W matrix, and that is added with input vector multiplied by U matrix. That is this representation. This is the current information. This is previous information. They are added, combined together with a bias. That went to the tangent hyperbolic activation function. That tangent hyperbolic activation output is becoming on hidden layer. And this hidden layer output will be used to generate output, or some of those information will be conveyed to next stage of hidden layer. Once again, this is more likely rigorous mathematical representation. This is more likely dimensional understanding of between input and, but actually this is a real mathematical, precise mathematical representation. Let me write down a couple of more equations before closing the class today. HT, hidden layer state, is tangent hyperbolic intermediate state. Intermediate state has a form of previous hidden state multiplied by W matrix plus UXT plus bias. This is more like a mathematical representation. Output is multiplied by full matrix plus multiplied by hidden layer plus bias. Actual output is soft max of OT. On Wednesday morning, please come to the class by 9 o'clock. We're going to buy a hamburger. One of the reasons I asked TA to buy hamburger for all of you is because Wednesday we're going to use more mathematics and mathematics. So it's going to be very tough to follow because I'm going to use all this equation to derive the backpropagation equations. So we have to be able to derive the gradient descent of the softmax function, tangent hyperbolic functions, and so on. A month ago, I was driving all those backpropagation equations, and I was able to show some chain rules. That is a little bit of baby, very, very easy, but Wednesday is going to be very. So maybe you may not need to know all those mathematical derivations, but I said that in order to use this generative model with more confidence in your big insight, I think if you have better understanding of this architecture and mathematics, you may be more confident while you are presenting or while you are doing the researches. I think this part is the mathematical description of recurrent neural network, and this is graphical representation expression of RNN, and this middle part is the mathematics used. One of them is softmax, and second one is tangent hyperbolic activation function. Once again, today, I use this RNN architecture because this is the really initial type of generative AI, mostly suitable for sequential data generations. And the recurrent, there is a name, recurrent, means the same architecture is used again and again and again until the final stage, time stage. During this propagation of hidden layer from time step 1 to time step t, we repeatedly use the W matrix, multiplication, multiplication, and multiplication. During the process, new X information is added together. So as a propagation, during the propagation up to the G space, more and more information will be added together. So W matrix has to be huge size, like a million by billion or billion by billion. And at each step, if you want to have an output sequentially, this hidden layer is converted to output using the softmax function. And whether it is a good generation or bad generation, we're gonna use the entropy function. And mathematically, it is written in this form. Number one, hidden layer at each time step is a tangent hyperbolic function of this is nonlinear function. Tangent hyperbolic is a nonlinear function. Input is 3 terms. First term is information conveyed from the previous hidden state. That is ht minus 1. We remember what was happening in the past and multiply by w. And we have to add additional information, data, that is current x input multiplied by u, and b is a bias. This is gonna go into the tangent hyperbolic function. That is becoming hidden layer. Actually, output of this each sequence will have form of yt. We're gonna use the softmax function. Why is that? Because the summation of all this y, y1, y2, yq, at each time step, summation of each element is becoming 1. That means this y is a kind of probability distribution. That's what. So output is a form of hidden layer plus bias. So if you at each step, if you have hidden layer, you multiply by matrix V, and by applying the softmax, we're gonna have yt. By comparing these two real data, we can define the loss function. If you have loss function, we can apply the backpropagation. Backpropagation means we have to determine W matrix, U matrix, and V matrix to minimize the loss, to minimize the entropy. That means to minimize the discrete distributions. I feel sorry that if we move into the transformer model, this matrix, this mathematical description and explanation is much, much more complicated. So be patient. At each time step, if you feel sleepy or you are not paying attention to me, I'm going to buy kimbap, hamburger, and pizza, and homework. And initially, I was not intended to give you homeworks, but this is really bold and long processes. So each step, I'm going to give you homework 1, 2, 3, 4. So, and some point, this W matrix is a hamburger, something like that. At the end, G is a kind of grade A, B, C, D, E. But just kidding. Okay. Thank you for your attention. This is the end of my class.